Okay, imagine you were given a differential equation or you were given a derivative, let's say dy dx equals 2x, and someone asked you, well, what was the equation you started with? You have a little bit of a problem because we could say that it's y equals x squared, and that's one answer, and it's correct because the derivative of y is dy dx and the derivative of x squared is 2x, but it could also be y equals x squared plus 1. Or maybe it was y equals x squared minus 1. So you can see here the derivative of this is also 2x because the derivative of 1 is 0. The derivative of negative 1 is 0. So basically we have a whole family of functions where the derivative is 2x. Well, we have a graphical way to represent those functions, and it's also a graphical way to represent the slope. So imagine you had the equation y equals x squared. You would have a parabola. Okay, and then imagine you actually were just looking at the slopes. So let's say at x equals 1, negative 1, etc. I look at the slope of this point. I could draw a little tangent line to represent the slope of the tangent line, the derivative 2x. The slope when x equals 1 on the parabola is 2 times 1 is a slope of 2. So I'm drawing a little slope segment that has a slope of 2. Well, if I graph y equals x squared plus 1 and graph that, at this point, which would be 1 comma 2, it would have the same slope as this. So I could draw a little tangent line showing that it also has a slope of 2. The slope right here, the origin, is 0. The slope at 0, 1 would be 0. And if I went through and graphed the whole family of functions and put little tangent lines on, then what I would actually have is something called a slope field. Now it would just have the tangent lines itself, and it represents a whole family of functions with a certain derivative. So I have an example of a slope field right here on the notes. And you can see all the little tangent lines showing. So there are two different kinds of things we can do with this, really, well, lots of things, but one, you could actually just draw a solution curve. And if we go back to the picture I had, this y equals x squared, that's one solution to this differential equation. So it's a solution curve. It also happens to be the solution curve that goes through 0, 0. I could say it's the solution curve that goes through 1, 1. The solution curve that goes through 1, 2 is y equals x squared plus 1. So one thing you could be asked to do would be to draw a solution curve. So this is a slope field of a little bit more complicated differential equation. It was dy dx equals xy. So the solution curve through 0, 1 is shown. I'm going to draw the solution curve through 0, 2 as well. Now, I don't actually know what the equation is, but it doesn't mean that I can't make it fit into this slope field and make it match. When you're drawing a solution curve, you don't want to go against the slope fields. If I look to the right of this point right here, 0, 2, I can see that the slopes are positive, and it appears that the graph is concave up. So I would follow that pattern up to the right. To the left, the slopes are negative, and it still looks like the graph is concave up, so I'll just follow that pattern up. If I draw the solution curve through 0, negative 1, then you can see that to the left the slopes are positive and it looks concave down, so I would draw my graph looking like that. To the right, the slopes are negative and it also looks like it's concave down, so I'll just follow the pattern down. What I don't want to do is, let's say my solution curve had a point out here. You can't do that, and it clearly doesn't match the slope field, but I see that sometimes on graphs and I'm not really sure what they're looking at. Now you can't really see, but you've got a whole bunch of zero slopes that are sitting on the x-axis. So let's say that we had a solution at 0, 0. Well, if I go to the right, it's going to have a 0 slope. If I go to the left, it has a 0 slope. So I could be drawing a solution line that looks like this. Things you don't want to do. If your slope is undefined, you may not be drawing points. It could be that there's a vertical tangent line, but the slope is really undefined at that point, so we generally leave those blank. So one thing you could be asked to do besides drawing a solution curve is actually to draw a slope field. So for the first equation, I'll write a little bit bigger, is dy dx equals x plus 1. And there are lots of different methods for this. What I like to do is actually just look at it and say, okay, there are x's in this equation. There are no y's in this equation, so the y values really honestly aren't going to matter. It's going to just depend on the x values. Whereas for this equation up here, the x's mattered and the y's mattered. So what I would do is for every x value I have, I'd figure out what x plus 1 is. So when x is -2, -2 plus 1 is a -1, and I'll just write a little -1 down there. Let me draw a line. When x is -1, then I'll do -1 plus 1 is 0. When x is 0, 0 plus 1 is 1. When x is 1, 1 plus 1 is 2. And when x is 2, 2 plus 1 is 3. So I'm going to draw small segments that have a slope of -1 all along this vertical column. So to do that, I think, okay, I'm going to have a slope going through this that's down and to the right 1, a -1 slope. So I'm going to have my slope head to the next point. My goal is to draw a bunch of negative little parallel line segments. A slope of 0 we know is horizontal. A slope of 1 will go up 1 and over to the right 1, and I'll draw a bunch of parallel line segments. A slope of 1, an x value of 1 gives us a slope of 2, so that would be like I'm going up 2 to the right 1. So it's going to be a little bit steeper. For the slope of 2, it's even steeper. So I'm just going to try to draw something steeper and try to keep it parallel. So that's one way, just keep track of your x values down here, and the y values did not matter. Some people actually make an xy chart, so we would say it's x, y, and then I'll add an x plus 1. And they just pick points. So at 0, 0, the x value plus 1 is 1. So at 0 you would draw a line segment with a slope of 1, and they would just go through as many points as they needed until they got the pattern. Now it's interesting to note you should be able to tell what kind of curve we have here. If I look at the equation y equals x squared plus x, then the derivative would be dy dx equals 2x plus 1. So I'm going to put a little 1/2 here, and that makes it a 1x plus 1, which would give us this differential equation. The point is, you're seeing something linear here, which means I'm going to have something quadratic as a solution, and you should be able to see that the quadratic functions would fit into this. It looks like a parabola would fit in. So if I were to draw a solution curve, let's say I'm going to draw a solution curve that goes through -1, -2. Then I'm going to follow the lines up to the right, and you just want to do your best. Just don't cross over a slope line. And that could be one possible solution curve. For this next slope field, it's dy dx equals 2y. So this time the y's are going to matter, not the x's. So I'm going to go along and figure out what 2 times y is. So on the x-axis, y is 0, so that would be 2 times 0 is 0. When y equals 1, it's 2 times 1, so it's 2. When y equals 2, 2 times 2 is 4. In the negative y's, I have 2 times -1 is a -2, and 2 times -2 is a -4. So the easy slopes are going to be these. So a slope of 0, and I'm going to draw horizontal line segments. A slope of 2, remember you're going up 2 over 1, and you want to try to draw a bunch of parallel lines. A slope of 4, that's much steeper. A slope of -2, so down 2 and to the right 1. and then it's even steeper but negative for a slope of -4. And maybe you can see the solution curve. If we had a solution curve right here, it would go down to the right, and it would eventually, I think, flatten out as it goes to the left. We might have an asymptote right here. So this slope field is only dependent upon the y values, where this slope field is only dependent upon the x values. And if you ever have to match a slope field, you can tell that by looking. If you look at a row here, they're all the same. So x clearly doesn't matter. That's true for every one of these. If you look over here at the top one where x's did matter, they're always changing, but the y's, the columns instead of the rows, are the same. So y did not matter. Here x did not matter. For our last slope field, it's dy dx equals x plus y. So the x's and y's do matter. So what I'm going to do is just mark my y values here. So I have 0, 1, 2, -1, and -2, because it's just a y, I'm not doing anything to it. My x's are -2, -1, 0, 1, and 2. And to figure out the slope, I'm going to look where these two numbers come together. It's x plus y, so it's the x value and the y value. So 0, 0 is easy. 0 plus 0, 0. The other zeros would be -1 plus 1. So there's a 0 slope here. -2 plus 2. There's a 0 slope here. 1 plus -1, a 0 slope. And 2 plus -2, a 0 slope. And you want to look for patterns. If you don't see the patterns, that's okay. Just draw slopes until you actually do see a pattern. So let's say I'm picking random points. This is an x value of 0 and a y value of 2, so that's a slope of 2. This is an x value of 0, a y value of 1, so that's a slope of 1. And there isn't a clear pattern yet. An x value of 1, a y value of 0, that's a slope of 1. Here, it's 2 plus 0, so a slope of 2, a little steeper. If I look down here, a slope of an x value of 2, a y value of -1, that adds up to 1. And you might see this diagonal. These all had a slope of 1, so I checked this one. -1 plus 2, that's also 1. So that worked out. And you start wondering, do the diagonals work? 1 plus 1 is 2, and they do. 2 plus 1 is 3, even steeper. 3 again, and then even steeper. If I look over here, -1 plus 0 is a -1. 0 plus -1 is also a -1. 1 plus -2 is -1. -2 plus 1 is -1. So the diagonals are always going to be the same. This would be -2 plus 0, so steeper. Steeper still. And then very steep. So you have all different kinds of solution curves for this one. If you actually put a dot here, then it's going to go down to the right, stick with it. It could look linear. If we put a point here, we want to know the curve that goes through that point. It's going to go up here. Down over here, it's going to level off and then head towards that line. Over here, if I put a point here and I want to draw the solution curve, it's going to go down, and it appears to slowly be bending up that way. So there are all different kinds of solution curves for this differential equation. And that's an introduction to slope fields.